Welcome friends to the Formula Engineering classroom, and in this new lecture of fluid mechanics we'll understand the concept of kinematics of fluid, and in this section we will understand the concept for approach for flow and fluid acceleration, or simply you can say that flow acceleration. So before going to depth in this topic, first we have to understand the concept of, or first actually we have to understand the meaning of term kinematics. So actually kinematics is the branch of mechanics that simply dealing with the motion without considering any forces that are responsible for the motion of that system. Means actually in this case we are not considering any kind of force or energy which is responsible for the acceleration or deceleration of fluid here. So here in this case we will simply analyze the motion of fluid, and that's why we are dealing with the kinematics of fluid. Okay, so the term actually kinema means motion. Actually this is a Greek word. This is defined as motion. Okay, so kinematics is simply, we can say that it is the branch of mechanics that is dealing with the motion without considering the forces. Now kinematics of fluid, especially we can say that there is motion of fluid or velocity of fluid or acceleration of fluid are defined at a point. What is the sense of this term? So actually let's suppose if we have some solid body, let this is our some solid body. Okay, and this body is moving with the velocity v. So I think every point in this body has the same velocity v, because they have no relative motion to each other. So the every point or every particle on this solid body has the same velocity, that is v. But in case of fluid flow this is not happening. Like let's suppose there is a pipe here. We are considering a pipe here. Sorry, we are considering a pipe here, and in this pipe some fluid is flowing. That we are saying some fluid is flowing here. Okay, now obviously at the pipe wall the fluid velocity is zero because no slip condition. So at the pipe wall the velocity of fluid is zero, but at the center line the velocity is maximum. So means here there is relative motion between the fluid particles. So in case of pipe flow you can draw the velocity profile like that, and we will understand this profile in the next sections or in the fluid mechanics or next lectures in the fluid mechanics. So here we are defining the velocity profile, and it's showing that there is the velocity of different particle is different in this case. Means the fluid particle is actually having relative velocity in this case. Okay, so in this case, so we can say that that is in case of a fluid the concept of velocity and acceleration is actually defined at a point. So in Cartesian coordinate system we can say that, like let's suppose if we are saying this is our Cartesian coordinate axis system, this is our x-axis, this is our y-axis, this is our z-axis, and let's suppose if I'm considering, just a minute, so let's suppose I'm considering a fluid particle here. Okay, so first of all we have to define the position of this fluid particle. So position of this fluid particle can be defined by the position vector. So we can say that the position of this particle is actually, we can say that this is defined by position vector r, and position vector r can be written as, so obviously in this case in the x direction the position is x here, in the y direction the position is y here, this is y here, in the z direction the position is z here. Okay, so the position vector r can be written as, that is r is equals to its x I cap, y j cap, and z k cap. This is the position of this particle. And let's suppose this particle had some velocity. Okay, so let I'm saying the velocity is v. In any direction, we are saying some random direction, the velocity is v. So that velocity vector v will also has three component in the respective x, y and z direction. And we can present like that. Let if I'm saying, so let I'm saying this is the velocity vector v here. Okay, this is the velocity vector v here. And this velocity vector has three components. So we can say first that is in x direction, and we can define this is u. In the y direction we can define this is small v, and in the z direction we can define this is w here. Okay, so this velocity vector have three components u, v and w in the respective x, y and z direction. So the velocity of this particle can also be present like that at a point, that is v is equals to its ui, vj and wk. Okay, so here capital V is the resultant velocity and it has component u, v and w. Now similarly, like velocity, we can also define as acceleration. So let's suppose if we are saying a is the resultant acceleration, then it has three components, that is component a or acceleration ax in the x direction, ay in the y direction and az in the z direction. So we can also represent or write the acceleration like axi plus ayj plus azk. So here I think the point is clear, that is the velocity and the acceleration in the fluid is actually defined at a point, or it is a point criteria. Okay, now so to analyze the fluid flow we have actually two approaches. First one is the Lagrangian approach and second one is the Eulerian approach. So let first we try to understand the Lagrangian and Eulerian approach here. So first I am defining Lagrangian approach, Lagrangian approach, and second I am defining Eulerian approach. Eulerian. Oh, actually, this is Eulerian approach. Okay, so there are two approaches, Lagrangian approach and Eulerian approach. Okay, so let's try to understand this one. So first, in case of Lagrangian concept, so we can say that actually Lagrangian concept is a particle based concept or particle based approach. What is the sense of this term? So let's suppose if we are saying, in this case there is some fluid particle here, we are considering some fluid particle here. So in this case, the velocity of this fluid particle is actually the function of x, y and z, and the space coordinate are also the function of time. Means we can say that here the velocity is the function of x and x is the function of time, y is also function of time, z is also function of time. Okay, so in this case we are saying, so in this case when the particle is moving, we are also following this particle during this course of motion. Means let's suppose if this particle is moving like that, in that case we are following this particle during the course of motion. So actually we are following a particle in this case. So in this case, as the time is going to be changed, the xyz is also going to be changed, and here we are analyzing the fluid flow based on this particle flow. So when the motion of this particle, you can say that, let's suppose if we are saying we want to analyze the traffic of Delhi for some particular part, let's suppose from IIT Delhi to Hojkas metro station. So in that case we are hiring a car, or let's suppose we are hiring an Uber. So when we are moving in the Uber, so in that case we are following, or we are simply moving with this car in the traffic, and in that traffic every vehicle is presenting the different particles. So in that case, when the Uber is moving in the traffic, so this type of pattern is generated here, or the motion will be like that. So means in this case, in case of Lagrangian technique, we are simply following a particle during the course of motion. In that case, the space are the function of time here. So this is the particle based approach. In case of Eulerian concept, this is point based approach. Means we can say that if similarly, if we want to analyze the traffic of Delhi from IIT Delhi to Hoj Khas metro station, in that case we are not hiring any car. In that case, let's suppose we are at some red light. So when we are standing at nearby the red light, then we are viewing the different cars moving from that red light. So in that case, the space functions are, sorry, the space coordinates are not the function of time. Actually the velocity is the function of space coordinate and time. Means Eulerian approach is a station approach or a point approach. Means we can say that in that case the velocity is the function of x, y, z and time. So this is a station approach. So means in this case we are considering one station here and some another station here, and we are viewing that particular particles that are moving from these stations. So in this case the fixed station we are considering. So the here the Eulerian approach is simply defined as a point. Means we are at a point, and in this case the particles are coming in and going out from different points. So the Eulerian approach is the point approach and the Lagrangian approach is the particle approach in this case. Now the problem is that actually the answer from the both the approaches is the same. But the problem with the Lagrangian technique is that is the single particle didn't define the complete flow. That's why this approach is insignificant, and actually this approach is laborious approach. That's why we are simply following the Eulerian approach. So in throughout the fluid mechanics we will follow the Eulerian approach. Means we will mark some station 1 and we will mark some station 2, and we are saying the velocity at the station 1 is v1, the discharge is q1, then we will define at the station 2 is the velocity is v2, like that. You are doing these things in your engineering. Actually you are marking the stations and you are analyzing the things. So actually that approach is Eulerian approach. Okay, so in this next section or in the coming lectures we will always use the Eulerian approach here. So based on the Eulerian approach we can define the acceleration of the fluid. So let's start to analyze the acceleration of this one. So based on Eulerian approach we are simply saying that is velocity is the function of x, y, z, that is space coordinate, and time. So if velocity is the function of x, y, z and t, so that's why we can also say that as we are writing there is v is equals to ui, vj and wk, then we can say that there is u is also function of x, y, z and t. Similarly v is also function of x, y, z and t, and w is function of x, y, z and t here. Okay, so how can we say that u is the function of x, y, z and t? So we know that is u is the velocity in x direction. So let's suppose here I'm considering a variable area duct. In this case for this duct the area is varying here when we are moving in this direction. It is also variable here, it is also variable in this direction. So we are defining this is a variable area duct here. Okay, and let's suppose we are fixing our coordinate system and we are saying this is our flow direction x, let's suppose this is y and this is z here. In this case I'm saying, so if at this cross section that I'm drawing the flow pattern, so obviously at the wall the velocity is going to be 0, okay, because there is no slip condition here. But at the center the velocity is going to be max here. So at we can draw it like that. it's okay. So here and here the velocity is 0, but at the center line the velocity is max here. Similarly, in this direction we can say that is in z direction. So in the z direction at this point and this point, the velocity is 0, but it's going to be max in center line. So you can see here the velocity u is the velocity in x direction. So this is varying in the y direction. It is maximum at the center and it is 0 at the solid surface or the wall of this duct. And similarly, it is also varying in the z direction because it is maximum at the center and it is 0 at the wall. And it's moving in the x direction. Then obviously in this case, as the area is going to be increased, so in that case we can say that there is velocity is going to be decreased according to the continuity equation. We will discuss that continuity equation later. So here we can also say that there is at this cross section, we can also draw it, and we can say that the pattern will look like this one. The pattern will look like this one. Okay, it will look like this one. So obviously in this case the center line velocity is also going to decrease in x direction as area is increasing. So from here I think it is clear that is u is the function of x, y and z. Means you can vary with x, y and z. Now if the flow rate is going to be changed, then at the same cross section with respect to time, this center line velocity is also going to be changed. Means if the flow increases, then in that case at the same cross section with different time or at some time interval the velocity increases, or when the mass rate is going to be decreased, in that case that at the same cross section at the different time the velocity is going to be decreased. Means the u is also the function of time here. Similarly, we can define that is v and w are also the function of space coordinate and time here. Okay. So as we're discussing here, that is as u is the function of space coordinate and time. So we can write, let's suppose here I'm writing again, it is that is u is the function of x, y, z and t. So the total derivative we can write in this case, that is du. So du will be equals to del u by del x dx plus del u by del y dy plus del u by del z dz plus del u by del t dt. Okay, so we are defining the partial derivative in this case we are considering. So here we are defining this is what? This is total derivative of u in this case, and u is the function of space coordinate and time. So if I'm dividing this du with dt, so you can see here du by dt. So as u is the velocity in x direction and it's changing with respect to time, we can define it will present the acceleration in x direction. Okay, so from here we can write, as we are dividing dt here, so we will also add dt in this side, right hand side. So we'll write del u by del x dx by dt plus del u by del y dy by dt plus del u by del z dz by dt plus del u by del t dt by dt. Okay, so in this case dt by dt is going to be 1 here, so this is out in this case. Now we can write this is, that is ax. So ax equals to, now here dx is going to change with respect to time. So dx, we are defining x coordinate, so this is presenting in velocity, and actually this is presenting velocity in x direction, that is nothing, it's simply u here. Okay, so this is defining u. Similarly here dy by dt is presenting the v and dz by dt is presenting the w here. So from here we can say that is this term is presenting u, this term is presenting v, and this term is presenting w here. So we can rewrite this equation and we can write this is u del u by del z plus v del u by del y, sorry this is del x actually, plus w del u by del z, and plus I think this term is out here, so we can write this is del u by del t. So this is presenting the acceleration of fluid particle in x direction. Okay, as we defined, that is u is the function of space and time. So this is presenting the acceleration in x direction. Similarly, we can say that is acceleration in y and z direction. We can write, that I'm writing here, that is acceleration in y direction. So I can write this become u del v by del x, v del u by del y, w del v by del z, and plus del v by del t. And similarly, acceleration in z direction we can write, sorry, this is w, oh sorry, this is u, actually not w, this is u del w by del x, v del w by del y, w del w by del z, and plus del w by del t. So this is presenting the acceleration in z direction, this is presenting the acceleration in y direction, and this is presenting the acceleration in x direction. Okay, so here we define the acceleration in all three directions. So as we know the acceleration in all three directions, so we can say that is the total acceleration can also be written as we written it before, that is a is equals to, this is ax I cap, ay j cap, az k cap. Okay, this is the total acceleration. Now we are completely familiar with this term, that is del u by del t. We know this is acceleration, but what kind of acceleration is this one? That is u del u by del x plus v del u by del y plus w del u by del z. So this is also presenting an acceleration, and we are familiar with this one. This is the acceleration. So there are two terms in this equation. Okay, two terms here we are defining. So we know this is defining acceleration with respect to time, this is defining, here we are defining acceleration with respect to time, this is we are defining acceleration with this time. But these terms, this one and this one, these are defining acceleration with space coordinates. So here we are defining the criteria of convective and local acceleration. Okay, so guys, in this given equations, the term del u by del t, del v by del t, and del w by del t are defined as local acceleration. Okay, this is defined as local acceleration, and the term u del u by del x plus v del u by del y plus w del u by del z, then u del v by del x, v del v by del y plus w del v by del z, and u del w by del x, v del w by del y, and w del w by del z are termed as convective acceleration. They are defined as convective accelerations. So what is the sense of local and convective accelerations? So let's try to understand this one. So let again I am considering a variable area duct here. So here we are defining a variable area duct. Okay, this is our variable area duct here. And according to Eulerian concept, we are considering two stations here. So this is our station 1 and this is our station 2. Okay, now, so let's suppose we have two stopwatch here. One is here, second is here at different stations here. So first of all, when we are defining the local acceleration, that means that acceleration is occurring at the local point, or we can define that acceleration is occurring at that particular station with respect to time, or it is defined based on the time. Means let's suppose if I'm saying that at t equals to 1, t equals to 1 means at I'm defining at the first station, that I'm saying the velocity is 1 here. Okay, now for the next second that I'm saying t equals to 2, the velocity is going to be at 3 here. So in this case, at the first station, as the time is going to be changed, so at the same station or same cross section at the one here, the velocity is going to be changed here. So in this case, the fluid is accelerating locally here, or it is accelerating with respect to time here. Okay, now let's suppose if I'm saying at the station 2 here at t equals to 1, that if I'm saying the velocity was 0.5. Okay, this was 0.5, and at t equals to 2, that velocity is, let's say if I'm saying this is 2 here. So in this case, at the station 2, we are first talking about the local acceleration. So at the station 2 only, you can see here at the time is going to be changed at this cross section 2 or this station 2, the velocity is also going to be changed, or it's increasing. So this type of acceleration that is completely based on time and that is occurring at the local point is defined as local acceleration. But if you noticed between these two stations, and I'm saying at the same time here, if I'm saying at t equals to 1 here and t equals to 1 here, in that case you can see here the velocity is different. Here at the station 1 the velocity is 1, and at the station 2 the velocity is 0.5, means the velocity is going to be decreased, and this is at the same time, and this is occurring over the space, means actually this is occurring over the x direction, means here the acceleration is happening over some space, and that's why we are saying this is convective acceleration, because something is conveying here over the space coordinates. So this is defined as convective acceleration. So guys, we can say that that is actually this one, that is over the time interval we can define this is local acceleration. This is local acceleration, and combining these two, or you can also take the values of 2 3 and 2 2, these combining values I am defining convective acceleration. Okay, so I think the point is clear. So there are two type of acceleration term in our equations. One is local and another one is convective acceleration in case of fluid flow. Okay, now we can also add them all values. So we can say that there is total acceleration A can be defined as, that is ax I cap, ay j cap, and az k cap, and we can put the values of ax, ay, and az here. So here we can write this is u del u by del x, v del u by del y, w del u by del z, plus del u by del t I cap, plus u del v by del x, plus v del u by del y, plus w del v by del z, plus del v by del t j cap, and plus u del w by del x, v del w by del y, w del w by del z, and plus del w by del t k cap. Okay, so we can convert this differential form in the vector form. So first let I'm making or converting this individual acceleration, that is ax, in vector form. So we can write here that is ax we defined, that is u del u by del x, v del u by del y, w del u by del z, plus del u by del t. So I think in vector form we can break this term like that, that is I can write this term about like ui plus vj plus wk dot product of del u by del x plus del u by del y plus del w by del z. Okay, here is actually I cap, here is j cap, here is k cap. Okay, plus del u by del t. I think we can, so if you taking the dot product of this one, you will get this term here. Okay, now I think we can present this ui plus vj plus wk like capital V here. So this is dot product. Now actually this is simply defined as grade u. This is grade u here, or we can say this is del u. So what is the sense of del here? So actually we can say del is simply presenting del by del xi, del by del yj, and del by del z k cap. Okay, this is our del here. So I'm writing this is v dot del u plus, so actually this is del u by del t plus del u by del t. Okay, so this is our ax here. Similarly, we can write ay is equals to what? So ay we can write v dot del v plus del v by del t, such a small v, and az like v dot del w plus del w by del t. Okay, these are the individual acceleration in the x, y, and z direction. So when we put this value ax, ay, and az here, so this equation becomes, so that I'm writing here, that is a will be equals to v dot del u plus del u by del t I cap plus v dot del v plus del v by del t j cap plus v dot del w plus del w by del t k cap. Okay, now so by combining all and using the vector properties, we can write, that is actually this is v dot del u I cap, v dot del v j cap, and v dot del w k cap. So combinedly we can write this term like, so we can write this is v dot del in bracket v, this is actually the vector property, plus, so actually you can see here this is del u by del t I, del u by del t j, and del w by del t k here. So we can write this term be like del v by del t. So this is our vector form of acceleration of fluid flow. Okay, so I think the points are clear. So guys, if you like the lectures, please like the videos, subscribe the channel, and comment your doubts, and share the knowledge as much as you can. Take care of yourself. See you in the next lecture. Thanks for watching.